know is Marco Iglesias, and he did his PhD at the University of Texas at Austin in 2008, and then he moved on to Warwick, where he was working together with Professor Stewart. And then he continued on to the University of Nottingham as an assistant professor, and recently he went to become an associate professor at the University of Nottingham. And today he will be speaking about this Ensemble Kalman Inversion, and he has been working a lot on basically filtering and Bayesian inversion. And thank you so much for accepting the invitation to give a talk. You can start.
Thank you very much. Thank you very much to all the organizers for the kind invitation. I apologize that I cannot be there in person due to COVID reasons, but thank you very much again. And what I would like to talk today is about LevelSet parameterizations within the Ensemble Kalman Inversion. And this is going to be a very applied talk. I'm not going to discuss anything methodologically new, but mainly the efforts that applying some methods that we developed, that we introduced several years ago. And we're trying to push this method towards applications, in particular in manufacturing engineering, geophysics, and medical imaging, among others. This is work that involves Michael Trejakov, also from mathematics here at Nottingham. From the manufacturing side, Michael Matvis, Andreas Endrubai, and Andy Long. And then for the geophysical application, my collaborators are Andy Binley from Lancaster, Michael Tso, now in the UK Centre for Ecology and Hydrology, some colleagues from the British Geological Survey, Paul Wilkinson, Oliver Kuras, Jonathan Chambers, and for the medical imaging application, Teddy McGrath, who was a research fellow, and my colleague Sue Francis from the Sir Peter Mansfield Imaging Center. And I would like to acknowledge also funding from the EPSRC Hub for Composite Manufacturing, as well as Kidney Research UK. So the aim of the aim of what we're trying to do with the LevelSet parameterization for Ensemble Kalman Inversion is essentially to do Bayesian inversion to solve inverse problems, where the goal is to infer unknown regions in PD-constrained problems. Now, for most of these problems that I will discuss today, these regions that we want to infer represent discontinuities of physical properties, which are mainly coefficients of the PDE. So we have a PDE that describes some physical process, and these regions or known regions are discontinuities. And we're specifically focusing on applications where these regions are anomalies or defects or some malignancy in its biological tissue, for example. So the idea is very simple, and I can describe it in a few words. So essentially what we have is parameterize these unknown regions with a LevelSet function, and then replace this kind of geometric inverse problem in terms of estimating a function that we're going to truncate to determine the regions of interest, and then potentially add variability within each region to make the problem realistic. We're going to work on Gaussian priors on the LevelSet function, and then the objective is to approximate the posterior of the parameterized problem with Ensemble Kalman Inversion. I will tell you why we choose Ensemble Kalman Inversion, in addition to the fact that this is something that we've been working for quite a long time. And I will discuss the applications that I mentioned earlier. So let me start with the motivating example, and this is a relatively new inverse problem. It arises in resin transfer model, which is one of the commonly used process to produce composite materials. Composite materials are widely used in aerospace, automotive, and marine industries. So most of an airplane is made of composite material, which are high performance, lightweight materials that can accommodate complex designs. And the manufacturing involves various aspects. One is aromatic fiber placement, where a robotic system, like the ones that you can see in the slide, places some fibers into a tool. So these layers of fibers make what we call the preform, which is a dry fibrous reinforcement. These fibers are packed into a mold, which is enclosed. Obviously, the mold has the shape of the part that you want to manufacture. So once it's packed into a mold, then you inject resin that fills this preform. Once it's filled with resin, it's allowed to cure at some temperature, and then once it's solidified, then you demold the part, and that's your composite. So the reason why we're interested in an inverse problem here is because there is a lot of uncertainty in the variability of this preform, of these dye conformance that comes from the misalignment or potential misalignment of fibers. So the preform, which you can see an example of a rectangular reinforcement here, it's a porous medium, okay? And the permeability and porosity of this porous medium is related to, again, to this alignment of fibers, how the fibers are placed. And because the robotic system is not perfect, that means that there might be some variability in these properties. And what we would like is, during the infusion of resin, we would like to capture this variability, characterize this variability, because that is critical not only in the injection of the resin, but in some cases this variability can compromise when it deviates from the nominal or the design value. It can compromise the performance of the material. So what you can see here in this cartoon is these pictures are the resin. So this dark area is the area that has been filled with resin, and it's not a straight front when it's supposed to be a straight front. And in some extreme cases, what happens is the resin will not fill some areas due to the very low values of porosity and permeability, and then it can create a defect. It creates a bubble, and then that's a defective part. In some of the cases, it could be very high, and then it will run across this area, and it will not fill. It will end the process before it actually completely fill the reinforcement. So what we have proposed is to address this as a way to have some non-destructive evaluation of these composite parts, which tend to be wasted a lot, is to actually collect data during the resin infusion and then try to infer these properties, and by doing so, flag some potential regions of anomalies. So the infusion of resin is modeled with the equations that you see here. So this is what FP for forward problem. So we have a Darcy flow, which is this second order elliptic equation, where the variable here in red, kappa, is the permeability of the preform, mu is the viscosity of the resin, and P is the pressure of the resin at a given position in the preform at a given moment in time. And that's defined in a domain T, which is changing, it's variable. So this is a moving boundary problem, where you see in this picture here, the moving front will be what is in the equations gamma T. So gamma T, the equation for the front, which is the interface between the resin and air, is described by another equation, which I'm writing here in a formal way, which can be understood in 2D, to have an ODE for the front. And that depends also on permeability and porosity. So we have two functions here, which are the dependent variables of the PDE system, which is the pressure and the front. And obviously we have boundary conditions and initial conditions. So these are the PDE, this is the PDE that constrains our problem. And the quantity of interest in this case that we're going to confront with measurements is the pressure at some locations on which we're going to deploy some transducers, and some locations where we're going to, or lines where we're going to measure the front. This can be done also with some camera. There are various ways to do that. So the inverse problem is to identify these quantities in red, the permeability and the porosity, kappa and phi, given measurements of this quantity of interest. And again, the idea is to, by the end of the process, be able to have some non-destructive evaluation of the composite part. So this is the motivation for this inverse problem, which we've been working with our colleagues from manufacturing here in Nottingham. So how do we formulate the inverse problem? So to formulate the inverse problem, let me introduce a forward map. So the map or the operator that takes porosity and permeability, which are, you can think of as the inputs or non-inputs of this problem, and maps it into the quantity of interest. Then we're going to consider we have observations eta from this quantity of interest, and I'm going to employ the Bayesian approach that consists on characterizing the posterior of these two properties given the observations of the quantity of interest, which we know is proportional to the likelihood and the prior. And again, employing the standard assumptions, I'm going to consider that these measurements are the evaluation of the forward map with some noise, which is Gaussian with mean zero and covariance sigma. Now, We need to bear in mind that here, kappa and phi are likely to be discontinuous. So this is the main challenge of this. We know that there is a design nominal value of these properties, and what we want to do is to be able to incorporate sharp discontinuities. And there are two ways to do that. One is to incorporate that through the prior, to come up with some clever prior that will honor these discontinuities. And the other one is to reparameterize the problem and use a level set function, which is what I will discuss today. So how can we use the level set approach to parameterize functions? So I'm going to introduce a function, psi L, function of x, which I'm then going to truncate to define a region. So for example, the defective region will be described by all those points for which this function is above some threshold lambda. So you see here in this panel, the level set function that I have a nice smooth function that I sample from some Gaussian. And I'm truncating this for values greater than 1, which corresponds to the effective region, so the blue region, with some mean around 0.4. And then for values that go below lambda equal 1, then I have the background region. So that allows me straight away to produce some random sample of a porosity in this case that will have a defect when the threshold is above lambda and the background value if it's less than that. And then obviously for being realistic, we can add some variability within the defect and outside the defect by introducing additional random fields. So summarize this porosity field that you see here in the right panel that comes from this truncating this level set function, and by adding a function phi1 in the defective region and a function phi2 in the non-defective region, which is you can see here. And then we can do the same for permeability. So we have made the problem more complicated from going from estimating 2 functions to estimate 5 functions. I'm going to consider log the log of all these functions to make sure they are positive when we do the inversion. So we have 5 functions to infer: log phi1, phi2, log kappa 1, kappa 2, and the level set function that will give me the interface between defective and non-defective. Now we're going to consider Gaussian priors for all these functions, phi1 to phi5. Gaussian functions with some mean and some covariance, and the covariance of choice is matern, with some hyperparameters, which, if you're familiar with this, it will be the smoothness parameter. In 2D, we have 2 length scales. You can potentially include an angle. You want some preferential direction, where the length scale will be longer along that particular direction. But in this case, just for simplicity, we have L in X and Y, and sigma J, which is the signal variance. So all these are hyperparameters of the prior for these 5 functions. So now we can reformulate the Bayesian inverse problem in terms of inferring these 5 functions and the hyperparameters given the observations. And that again applied by the rule. So if we look at what has been done, the idea of level sets to parameterize discontinuous functions, piecewise constant or piecewise continuous functions, is not new, and it was proposed in the 90s by Fadil Santosa to solve deterministic inverse problems. Now, to the best of our knowledge, the first work deals with this from the Bayesian perspective is this work with Yulang Lu and Andrew Stewart, where there's theory developed for very simple toy models. And I have to emphasize that this Darcy flow problem, this moving from problem, is a few orders of magnitude more complicated than the standard Darcy flow that you will normally see in GQ examples. This is more equivalent to a 2-phase flow when you are racing air. And that's, again, much more challenging, and it requires much more computational resources to solve than a simple Darcy flow because of the moving front. And the reason why we adopt this setting of moving front is because in the industry for composites, there is software that allows you to solve for this within the application for the resin transfer molding that I described. So I just wanted to make this comment. Going back to what has been done in terms of level sets in the Bayesian setting for inverse problems of this kind, for toy models, there is some theory and some examples. where this has been done. And then we quickly realized that incorporating the hyperparameters of the priors, assuming that the level set is a Gaussian prior, it is a Gaussian, we realized that incorporating the hyperparameters was really important for accuracy. And that was done in this paper in a hierarchical setting where you have some metropolis within Gibbs to sample from hyperparameters and then sample from the functions phi. Now, there is another approach that can be done, and that comes from recognizing that Gaussian random fields can be also characterized with a stochastic PDE approach introduced by Whittle and then made more applicable by Lindgren in 2011, which each of these phi j's can be sampled from by solving this stochastic PDE, which involves well, the identity operator, the second order elliptic equation where the coefficients are the length scales, the smoothness parameter. I'm doing this in 2D for simplicity, but we obviously have extended this to 3D as well. On the right-hand side, we have a constant that depends again on the hyperparameters, the signal variance, the smoothness parameters. Here, gamma is the gamma function, and the length scales again appear here, and y nodes. So on the right-hand side, we have y nodes forcing this system, and if we prescribe y nodes in 2D, in this particular case, we will get a sample phi j that is a Gaussian random field with mean phi j bar, and covariance c theta, where c theta is the Matern covariance. So we call this the Whittle-Matern random fields. So that's fine. That's a nice way to sample from a Gaussian random field. You can use Kalman. But the interesting thing about this approach, the nice thing is that it creates this parameterization. This induces another level of parameterization. So we have level sets, but now each of these functions, including the level set, we're going to parameterize with this approach. Because you see here, I can put all these parameters, all the theta j's that comprises the L, the length scales, the smoothness parameter, the signal variance, all that theta j, in addition to the right-hand side and the mean, that defines a parameterization we call the Whittle-Matern parameterization that maps these hyperparameters and right-hand side into phi, which are the phi functions that I want to infer, and then that maps into, via the level set parameterization, into the porosity and the permeability. So we can compose all these parameterizations into one single map that takes all these unknown input, hyperparameters, and so on, into the physical properties. The other reason why we adopt and we employ this SPD approach, as opposed to, say, Kalman is because we have found that in some cases, it is quite important to make these length scales for the level set function to be random functions themselves. So we have Whittle-Matern with Whittle-Matern. So we have a deep parameterization to be able to account for spatially variable length scales. And I will show you the example where for which we need to do that. So that's the other approach, to go from sampling from these functions into sampling for this vector u. So if we think of the reparameterized problem, we can comprise the forward map F with the parameterization P, and then just redefine the inverse problem in terms of the unknown input u, given the measurements. Now we have the mapping of composed parameterization with forward map and put a prior in. And then there's nothing that prevents us from using Markov chain Monte Carlo, any fully Bayesian approach. Now, our experience with fully Bayesian approaches, which is what we've done in these papers, using Markov chain Monte Carlo or metropolis within Gibbs for the hyperparameters, is that we require using, let's say, preconditioning Crank-Nicholson MCMC. What we have found is that we need a lot of samples to be able to capture some meaningful statistics. And that has to do, obviously, with the high dimensionality of this problem. So this parameter, the right-hand side of this SPD, the y nodes, will be discretized on the computational domain, and for 3D will be feasible to do in a Markov chain, to do 100,000 samples or 1 million samples that we often require. Now, dimensionality reduction that can come from a Kalman expansion truncating that is also not a very good idea in this problem, because for the level set function in particular, doing that, chopping some modes of KL expansion will lead to leaving out a lot of defects that are meaningful for this application. So I will show you some examples to highlight what I mean. So we needed something simple, something that requires only a few samples, something that is robust, something that converts in a few iterations. So we had experience with Ensemble Kalman Inversion, and I'm going to specifically talk about the classical Ensemble Kalman Inversion, which consists of sampling from the prior, collect some J samples. We're talking about the order of 400, 500 samples at most. And then each of these particles, update these particles in an iterative fashion. So each of these particles is updated according to some formula that involves two things. One, the covariance, CUJ, the cross covariance between the unknown. So for each of these particles, UN bar is the mean of the ensemble. The cross covariance between the unknown and the evaluation of the forward map for each of these particles. And also the cross covariances between these predictions of the evaluation of the forward map for each of the unknowns. So those are the predictions. So as you can see straight away from this formula, which is not only very easy to implement, it doesn't require any sensitivity, any adjoints, or any derivatives of the forward map. The framework employs the forward map in a black box fashion. The cost is the number of iterations that this takes to converge. Obviously, we'll have to impose some stopping criteria and so on. The number of samples times the number of iterations. So we're talking about a few thousand forward model runs. It involves also regularization, a parameter alpha n. We call it regularization parameter for reasons that I will briefly discuss in the next slide. And it adds some noise. So this is the so-called perturb observation Ensemble Kalman inversion. So this is, again, what I would call the classical Ensemble Kalman inversion. The motivation for this classical framework, so I'm not going to talk about the method itself because it's been out there for quite a while. But essentially, the only thing that I would say is that it can be thought as a regularizer or as a Gaussian approximation within a sequential Monte Carlo approach. As a regularizer, what we can say is that these particles are samples from some distribution, which is Gaussian. So that can be seen from the formula. So these are samples from a Gaussian that has some mean and some covariance. Now, if I do a linearization around the mean of that Gaussian that is being approximated by these samples, it can be shown that that formula resembles the formula that you get by that I explicitly wrote here, which is nothing but a Levenberg-Marquardt type of algorithm, where these derivatives that you will see in Levenberg-Marquardt are approximated with cross covariances that you have here, essentially. So these derivatives are approximated with cross covariances, and essentially we have used this observation of linking this to have ways to select the alpha in a more or less efficient way. But essentially you can think of this as a regularizer that approximates the mean of a Levenberg-Marquardt algorithm in without using derivatives, with the observation that this is done. So if you think of Levenberg-Marquardt will be aimed at minimizing this misfit. Okay, the misfit between the observation and the predictions weighted by the covariance of the noise. But with Kalman, the difference with the Levenberg-Marquardt is that we are constrained with a subspace generated by the initial ensemble. So this has been known since we introduced this approach to inverse problems, that you start with an initial ensemble and everything you get out of it is always a linear combination of the initial ensemble, which could be detrimental, and I will tell you a bit more about it in the next slide. But that's essentially what it is. And the second view of Kalman inversion in the classical setting is to introduce it by a tempering. So you introduce some parameters, phi m, between 0 and 1. So the first one is 0 and the last one is 1. And essentially, if you think of intermediate measures between the prior and the posterior, so you know that if phi m is 0, that's the prior, and if phi m is 1, that's the posterior. So if you introduce these intermediate measures that you would normally do in sequential Monte Carlo, then you can relate by introducing this linearization here into this likelihood, where you can show that the formulas that you get, more specifically the particles, are particles from this Pn will be Gaussian approximations of this mu n. And the alpha n that comes in Kalman inversion is essentially the inverse of the difference between these tempering parameters. So the larger the parameter alpha, the smoother the transition between these measures. Now, there's no theory that makes convergence or anything like that. So these are just observations that we made to motivate the method and why it works, but we don't have a theory of why actually of convergence of any kind for this particular setting. Okay, I will talk about a bit more the recent methods that people have developed, but this is what we use. So a bit of history. This idea of Kalman inversion comes from the Ensemble Kalman filter that was proposed in the 90s by Evanson. Yes.
Hi, this is Raul. How are you?
Hi, Raul. How are you?
Fine. I have a question on the previous slide,
yes.
If you don't mind. You know, how bad is this this situation of having the span of the solution that you seek controlled completely by the original ensemble?
How bad is this constraint?
Yes. How detrimental is for the method that that limitation?
It's very problem specific, because essentially what happens is that if your prior is very poor, then everything will be in the subspace generated by those initial ensembles. So I would say it really depends on the application. For the case that we are using, we overcome this by reparameterizing, because you see most people use this directly on the physical properties. So this is basically a lot done for the RC flow, right? So if you think of porosity, permeability, that can be quite detrimental because you cannot go beyond your initial ensemble. So you don't capture the truth within the initial ensemble, which is what you would expect in real life, then you're not going to get anything sensible. So you need to augment this space, and there are ways to do that. So the non-classical IKI framework aims at addressing this by injecting more, modifying the formulas in a way that you take new samples, let's say. So it is quite detrimental. But I would argue that for what we're doing, because we are working on hyperparameters, then that helps us a lot to identify physical properties that are perhaps not constrained, not capturing the initial ensemble.
Because what I was thinking, maybe we can discuss it at some point. Is not now, but I was thinking that we have the multi-level version of the Ensemble Kalman filter.
Yeah.
And there, you actually have the ability to put a lot more samples in different scales. Right. And I believe that may be very useful to actually, in a non-parametric way, deal with this.
Indeed.
I thought, long time ago, but that could be something to follow up. Okay, thank you.
Yeah, no problem. So indeed, this classical version, first, well, we took ideas from Evanson, from Kalman filter in the 90s, and more in the form that we know now in the 1998 in this paper with Peter Jan and Burgers. And then I think Evanson moved to the oil industry, so everything happened in the context of parameter estimation in the petroleum applications. I have to point out this alpha n parameter is 1 in the classical filtering setting, because you go from prior to posterior in one go. Tempering ideas probably came a bit later, at least for these applications. Then we introduced this in a more generic setting for inverse problems, PD constraint inverse problems in this paper. And then we found the connections with the regularization techniques later on. And we also used in this paper, we used the LevelSet approach as a test example. And then we later in this paper with Neil, Chada, and Lassie Roinian and Stuart, we show that actually you do need to do these parameterizations to enhance the space of physical properties that you can capture with this approach. So another approach, this approach of looking at this from the sequential Monte Carlo was also quite useful in terms of learning ways to select this parameter alpha n. So we look at paper by Cantas and co-authors to see how this can be done, and we apply this already for resin transfer molding in very simple settings. And we have also a recent paper where we propose other ways to choose alpha n, which is the regularization parameter. That's what makes it efficient or not. If you converge in 100 iterations, that's something that you don't want. We are conversing a few iterations because the solver can take a few hours in 3D for three-dimensional problems. So I have to acknowledge there is more recent work on this. in particular, I have to point out the pioneering work of Claudia Schillings and Andrew Stewart, where they, looking at the formula in the classical way, if you take this, the inverse of this regularization parameter, so some discretization variable that you tend to zero, then they derive a system of SDEs for these particles, and that has led to a lot of work that allows us to understand more of the theory. There was no theory before, but because of these new frameworks, we understand a bit better. In particular, in the linear case, it can be shown that as t goes to infinity for these particles, then all the particles collapses into one that converts to this minimizer. And then this ensemble collapse, which is not very good in the sampling case, we don't want all the particles to collapse. In the asymptotic case, and they have ways to modify this, essentially by adding some additional terms to this equation that prevents this collapse. Obviously, they've done it in a rigorous way to have some theory, again, in the asymptotic case, and also Nichad, Andrew Stewart, and Shin-Tong, they have also some work done on how to modify the method so that you can then solve Tikhonov regularization and also prevent the collapse by adding this additional term. All this theory is beautiful, but all these asymptotic cases, they don't really tell me where to stop. I need, to just produce this in a finite amount of time and resources. So this is the issue. So let me going back to the classical setting to what we've done. Let me give you some examples of how to or what we obtain by applying this algorithm. Again, this work with our colleagues from the composite group at Nottingham. I'm going to start with the synthetic experiments. So we have, again, this setting for composite manufacturing, where we have this domain. We have injection of the resin at the bottom. So the injection gates, this is a computational domain that we use. These 6 dots that you see here are where we collect pressure, and these 7 lines are the places where we collect the front, measurements of front. So we solved this moving boundary problem using ANSYS Fluent to simulate these measurements from these sensors, and using as a truth this porosity and this permeability. Assuming obviously they are in the same location, this is the effective area of low porosity, and adding some variability by producing some random fields. Now, the prior, again, is a prior that we put on these hyperparameters and the right-hand side of the SPDE. And by pushing forward all these hyperparameters back into physical space, we produce all these samples. So we have 400 samples from this push forward prior that you can see here, with some mean and some standard deviation, that we have selected a threshold for the LevelSet function. Here, the LevelSet function will give me the effective and non-defective, as you remember. So we have played with the hyperparameters to allow for various sorts of variability. So some defects will have elongated features because have longer correlation length along the vertical direction, and some of the other way around. So we have played with it so that all the particles are to prevent from this situation with the collapse and so on. And the threshold is high to ensure that under the prior there is no knowledge of where the defect is. Then we have these synthetic measurements. I'm showing here pressure from 1 out of the 6 locations, and front location from 1 out of the 7 sensors. Again, synthetic measurements generated with the solver, with the same simulator that we're using for the immersion. For each of these samples, we run the simulator, and we produce some confidence intervals for the prior, which you can see here. So it's not that bad. But we do the posterior, so we run Kalman on the hyperparameters and all deep parameterization. We push forward into physical space to compute the posterior samples, and we start seeing that we get the shape of the defects that we had before. There is a lot of variability in samples still, because we didn't consider a very small noise to make it realistic. The posterior predictions, when I pick each of these samples and run the simulator forward for this, we get this nice uncertainty band. So everything works as we would expect. Well, obviously, it's synthetic experiment. Everything works well with synthetic experiment. Right? But let's do real data now. Oh, well, before I go into that, I haven't shown you actually the main results. So from this posterior ensemble, we can compute the mean of these particles, which is what I show here for the porosity and for permeability. So that's the mean of all the samples, from 400 samples, I think, that we use for this example. The standard deviation, where you can see that the highest uncertainty variability is around the interface, as you would expect. Now that we don't capture much of the background, we estimate the mean value. So the mean value is estimated very accurately, but there is not enough information from these 6+7 sensors to actually capture all the variability outside the effective region. But the defective area was accurately identified, I would say. Now, if you remember, well, we're inferring these parameters in this parameterization, but when we go one level up to the Whittle-Mather one and compute the random fields that then we later use from the truncated formula for the porosity permeability, there is one that corresponds to the levels. Right? So for the level set, which is what tells me whether I'm in the defective area or the non-defective area, because I have an ensemble for that, a distribution, a marginal for that, I can compute the probability that at a given point that's above the threshold, because above the threshold tells me that I'm in the defective area. So I can compute a probability map that tells me how likely it is that at a given point I have a defect. That's what we've done here, to show that indeed the almost 100% probability is inside the region where the defects were in the synthetic case. So that was very good, very accurate, very promising that we can actually do that in synthetic experiments. Now for real data, exactly the same setting, exactly the same geometry, but except that we have simulated data, our colleagues manufactured this composite part where they put some circular defects in the same area that we use for the synthetic experiment, and they lower the porosity there somehow, and then they infused the resin, and they gave us real data from the pressure transducer and the flow from sensors, and then we applied the same technique with the same price. And what we got is very encouraging results given that it's real data, and that involves inferring the two regions of low porosity that they engineer, and for standard deviation that reveals high uncertainty in areas where there was not supposed to be defect, and we can compute the probability map. Now, there are some areas that will need further investigation where they were not supposed to have this low porosity, but nonetheless, we capture that. And we know that this cannot be done, perfectly controlled, but we feel that this is a very successful example that with real data, we were able to capture these effects and characterizing the values of these with uncertainty. So going back to synthetic experiments, in 3D, we have done more experiments where we have a more realistic setting of a composite part like the ones that they will produce. And here is when we realize that when you have defects of this kind, like a circular defect here and a very long defect on the bend, which by the way is how this is likely to happen because of the bending, the fibers will misalign, and that's what you're likely to observe, together with some other defects. But if you do this in the classical, in the way that I showed before, where the length scales are constant, then with the length scale here, the vertical in this direction, the length scale will be very small or relatively small to capture this circle, but it will be able to capture something like this. So you need a length scale that is very high along this direction, only in this area, and relatively small in this area, in the circular defect. So we had to employ random fields for the length scale to have an additional level of parameterization to be able to capture this, and provided that we have a lot of data. So we're playing at the moment in this project how many sensors we actually need, because the engineers will ask, well, there is so many sensors I can deploy in the tool. Tell us how many we need to be able to capture them. So this is where we are at the moment, building a demonstrator in the lab to be able to provide some more insight on what is it that we can accomplish. So that's as far as this composite manufacturing application. We have also done some work on applying this to electrical resistivity tomography, which is a very canonical example of a geophysical inverse problem, very old one as well. And my colleagues from BGS and Lancaster, we apply this setting. So here, what we want to do is to infer the electrical conductivity of subsurface formation given measurements of voltage at some, so here the measurements are voltage on at some sensors, some electrodes. So we're going to place electrodes on the surface, and we're going to inject some currents, and there are various ways to do that. The dipole is perhaps the simplest one. So we have a positive and a negative source, and then you inject your current. That will create voltage differences that will depend on the electrical resistivity of the subsurface. We have applied this for synthetic experiments in 2D and 3D and various real data from real fields. And the one that I will show you today is what they got from applying this to Eggborough field, where they have, well, this is actually the picture of it. They have very well characterized sandstone stratigraphy. So they have medium, coarse, and fine sandstone. They have 3 different types of sandstones. And the idea was to apply this to surface ERT data, voltages from electrodes. And they have a very well, this is a very well characterized field with other imaging techniques. So applying to subsurface is always a bit tricky because you don't have a truth, right? So it's hard to kind of come up with a truth, but they have other imaging methods to do it. And I have to say, even though this is a very simple PDE, the way this is done, it requires a bit of thought. So you cannot just apply this to simple thing in MATLAB. So they have their software because it needs to be like a grid that is captures a very big domain to avoid boundary effects, and they have a very refined measure on the electrodes. So, anyway, so they have the ways to do it. Kalman inversion, because this black box is quite easy to use with this. So I will use it to characterize the 3 different zones with 3 different sandstones. Now, for simplicity, we assume the sandstone, the value of the different sandstones is constant. So kappa 1, kappa 2, and kappa 3. And also for simplicity, we have one level set function that defines the 3 zones. So if it's above one threshold, it's zone 1, and between these two thresholds, set 2, and between below this threshold, set 3. So we have 3 different zones. Obviously, there are some modeling constraints which kappa 1 and kappa 3 cannot have the same interface. But nonetheless, just we apply this to see what we got. And as I said before, you can produce, you have your hyperparameters, you map into physical space, and you can get your statistics from your samples from physical space. But you can also take the mean of the parameters and then map that into physical space, which is what they don't here because they like also to have like an estimate of the truth. So in this case, the estimate of the truth, which will be the mean of the parameters mapping to physical space, is what you see here with 3 different colors corresponding to the 3 different sandstone values that we infer as well, as together with the interface between the 3 different zones. And what's interesting to see here is that they compare this with the values at some boreholes. So here, this line, this vertical line that you see here corresponds to boreholes locations where they deploy 2 different things. One are gamma logs, that are these traces, and also ground penetrating radar through R3 and R4 cross ground penetrating radar. Now, what those are, it doesn't really matter, but essentially, what it matters is that what they see from these signals is that the values that we got from Ensemble Kalman inversion, at least along those 3 boreholes, corresponds to what we found. And recall, we are taking only measurements on the surface. So that was very encouraging. And essentially, for example, here you can see this negative spike at GPR, ground penetrating radar signal. You see at -5, they see this kind of lower spike corresponds to a very fine formation of fine sandstone that we actually capture with Ensemble Kalman inversion here. So that's very interesting to see. The second thing, the last thing that I want to mention briefly is the application to magnetic resonance elastography. So in this case, this is something
Sorry, Marco,
that, yeah.
Can I ask a question on the previous example?
Sure.
So just to understand this geometry that you show there on the right, on the
Yeah.
bottom right. So you're injecting currents and measuring voltages, everything from the surface, right?
Everything is surface at this point.
So the currents essentially enter through the surface and leave through the surface on another location, essentially.
That's
from
right,
high
yeah.
voltage to low voltage.
Yeah.
So how do you ensure that actually these currents, right, are going to penetrate up to this depth? This is what I don't get. What is incentive? I mean, if you look at the lines of the current here, how do you actually make sure that they penetrate? Because that's the only way you could actually have information to reconstruct the problem. At least that's what I've seen in other sort of inverse tomography. I mean, with the voltages location. So I mean, I've seen this type of reconstruction, just to be more precise, putting, for example, injecting in one side, looking at the voltages on the other, or I mean, having on one side on the other. But here you're doing specifically everything on one side, because of course you cannot penetrate to leave these things. But usually what happens is that the current goes in and out in a sort of small arc and doesn't penetrate up to that depth, but you are able to reconstruct things from below. So what is the intuition to understand that you can actually do this?
Well, first of all, I'm not 100% sure how they did I don't recall exactly what's the configuration of measurements. Where they show only a partial area where they, like a zone of interest, but they might very well did surface ERT on a larger domain on the surface to make the arc that you're mentioning.
Yeah, because I mean, if one put, for example, a measurement inside of a borehole and measures the voltage there, or puts a sink for the current, then I would understand it, because then you make sure that you penetrate up to that depth. But without it, it's difficult to follow. So thank you for the clarification.
Yeah, so definitely they know what is the spacing of between the two electrodes and what's the configuration of the placement, and they need to reach some level of depth. But I have to say that I am not showing here the measure of uncertainty. But if you were to measure the uncertainty, most likely that would be very high here. The variance will be higher, obviously, here as you go deeper in the formation, because of what you just mentioned. So there is indeed some geometrical aspects that they need to satisfy to have some confidence that the measurements that they take on the surface are meaningful.
Thank you, Michael.
So in terms of this application, magnetic resonance elastography, this is a work that hasn't been published yet. There will be an archive paper soon, but it's in review. Essentially, what we're looking is at viscoelastic model. So we send an acoustic wave into biological tissue, and we are focusing on kidney. An harmonic wave of angular velocity omega makes this biological tissue to oscillate at this angular frequency. The viscosity is raw for this tissue. And essentially, we have an acoustic wave equation with some parameters, G and lambda, the first and second lambda parameters. V is the amplitude of the displacement. Because this is a viscoelastic model, we have complex G and lambda, and obviously displacement. And therefore, we have an inverse problem that consists of inferring these two values, because these two functions are related to how stiff or how soft the biological tissue is. So elastography is essentially a tomographic way to do what doctor would normally do with palpation, to see whether there is some stiffness in the tissue that can be associated with some malignancy. So what we've done here, one of the interesting things about this inverse problem, I have to say, is that the measurements here as the entire solution of this PD, because when you put a patient in the scanner to do this elastography, and they measure with MRI the displacement of biological tissue everywhere. By everywhere, I mean as provided by the resolution of MRI. But you have a lot of data compared to the previous examples. You have only a few sensors or surface measurements and things like that. So that makes it also a bit challenging from the computational point of view. We can make some assumptions. In this case, this G is a complex function. So the real part of this is what we call the storage modulus, and the imaginary part is the loss modulus. And we've done some only synthetic experiments at the moment. This is a proof of concept kind of project, where we apply the same techniques that I just showed you before to characterize the stiffness inside the region of interest and outside as well. So we have a background area. We assume that we know the anatomy of the kidney, which is something that can be learned from other imaging modalities. So you know what the geometry, obviously with uncertainty, but you know the geometry. And what we want is only to find the stiff the stiffness within each of the different regions. In this case, we have the cortex here in blue, the medulla more or less in yellow-green, and the background. But with the LevelSet approach, we can characterize these malignancies that can come anywhere within the kidney. So we apply the same approach. We have different coefficients in different regions, and the LevelSet that will tell me whether I have some tumor. And in this case, well, we have posterior variance and same approach. And with synthetic data, everything works well. Again, we don't expect the same to work with real data, but with synthetic data, we get very encouraging results. High variance, obviously, always at the interface between the healthy and the non-healthy tissue. And we have also extended this to have also some synthetic experiments in 3D, because again, the thing with Kalman is that it's so easy to implement, that you can then just replace the forward model from a 2D to a 3D, and then everything kind of works in the same fashion. Obviously, it takes longer time, but we have also some results where we have our synthetic true, and then we get the posterior ensemble, we compute the mean, and then through these levels, we can compute a probability that at a given point, we are in the defective area. So here, for example, I show from the posterior ensemble what's the region of being the region in which the tissue is highly likely to be have a cyst. And in this case, all this red area corresponds to the region where this is greater than 90%, which corresponds to the true cyst location. So I mean, it's just to show that it actually works. So I hopefully have convinced you that there is strong evidence that using LevelSet parameterizations within Ensemble Kalman Inversion is a promising tool for inferring unknown regions in certain properties where we have some background value and some anomaly that can come from some defect or some sort of malignancy. Obviously, we recognize that Kalman inversion is only an approximation of a fully of the Bayesian approach. So there needs to be some assessment of how accurate we are. And obviously, these modeling assumptions that we have made, having only one defective area, can be extended to multiple level sets, something that has been done, as far as I understand, at least in the deterministic setting. There is no reason why we cannot incorporate other Bayesian approaches, potentially some form of model reduction. So the purpose of this talk was hopefully to get some colleagues to suggest other methods. If anyone is interested in this application or any of the applications that I discussed, or apply your methods or have all the suggestions, I'm happy to talk and collaborate. Thank you very much.
Thank you, Marco, for the very nice talk. Do we have any questions or comments?
Hello, there was a very, very interesting talk for me. I was curious if what would you have to say about using your approach on level sets and Kalman inversion actually for optimal placement of sensors? If you think that would be possible. I was specifically interested in the case where you had a complex geometry and you had some ideas about possible failure regions, and if you could, for example, incorporate your knowledge to try to find the best places to place your sensors and minimize the uncertainties about the failure regions.
Yes, there is some work we're doing from the very applied engineering setting, where we have some essentially some measure of performance for the not measure of performance, so measure how far the defect is, and then do basically Monte Carlo. This is essentially by Monte Carlo. So the answer is yes, we've done it with Monte Carlo. There is, I think, a paper in preparation led by other colleagues in engineering, and I think Michael Treja, essentially, where they have this measure of performance of how bad the defect is, and then use this essentially as a Monte Carlo way to say, okay, well, this is what we get if we use this approach, but we don't have anything really sophisticated. I guess the answer, another answer would be, Kalman gives you an approximation in posterior. So it depends what your criteria is for optimal sensor placement, right? So you have any kind of covariance maximization, Kalman could potentially help you by giving you a cheap posterior approximation.
Okay, thank you very much.
But I have to say, it's nothing that I have done about it.
Okay, we have one more question.
So thanks for the nice talk. So how does this compare to the deterministic approach to inverse problem, at least for the models that you targeted here?
Well, I haven't obviously done any formal comparison with the deterministic setting, because in the deterministic setting, you most likely need to do some variational approach, right? So that will involve, you need some sort of sensitivity or derivative of the forward map first, which is something that we don't have access, at least in the case of composites. We have a commercial software, we can just run it. I recognize that there is a lot of value in doing the variational approach, and if you convince the industry that they need to move towards that, they probably adopt it, and they will derive the attributes and sensitivities to do it variationally, and they will be easy to compare with a deterministic system. But another thing I have to say is that I don't see a straightforward way to incorporate this in a deterministic setting in terms of getting the sensitivities with respect to the hyperparameters of the prior. So here it's easy to sample from the priors and then just evaluate forward. We don't need to worry about sensitivity. So these deep parameterizations are not very easy to differentiate and to get all these derivatives that you will need to apply some sort of Gauss-Newton. But the answer
So
is
what you say is,
yeah.
So what you say is here using LevelSets plus Ensemble Kalman Inversion is much easier than doing the deterministic approach.
But yeah, but a few orders of magnitude much easier and much more flexible. Now, whether it's more accurate, we don't know. And whether it's more costly, because obviously with Kalman inversion, we need to have an ensemble. So if we had a way to do variational, and you can just completely say the map estimator and then just put a Gaussian approximation of the map estimator, that would be way more efficient in terms of computational cost.
Any more questions? So you used the SPD approach with this matern.
That's right.
So when you do this, what was the priors that you use for the hyperparameters? Or, I mean, for one of the examples, for instance?
We use some uniform priors for the length scales. Pretty much sure we use uniform priors for most of these
because it's new.
Yes,
because this new parameter, if you change that one, then you literally will get different powers, right?
I have to say the new parameter is fixed for these examples.
Okay.
So especially for the level set, it's not that crucial to have the smallest parameter being inferred. You will argue that perhaps to infer the variability, but we know that we cannot really get much of the variability within each region anyway. So, but for the level set, it is important to choose that. And I have to say, it's not easy to do kind of sampling of this hyperparameter. Well, it's easy to do the sampling, but it's not easy to generate stable samples. If you start just randomizing the smallest parameters, it's going to be a bit tricky that you don't get anything that is completely crazy in the samples. But for that reason, we fix it to a value relatively smooth that will give us the defect, the characterization of defects that we would expect in this kind of application.
But I mean, the higher you will go in the smoothness, then you would have a big nu, right?
Yes. We just
and
nu
that
equal
means
2.
that you will solve a very second.
We use a value of 2 or 3 in 2 dimensions.
Okay.
For the smoothness parameter, which is is quite high. You get quite smooth samples.
Okay, thank you. Any more questions? Okay, let's thank Marco again for the very nice talk.
Thank you very much. Thank you.
Lorenzo, are you there?
Hello. Hi. Yes, I'm here. Let me also open up my camera.
Welcome.
Okay. Can you see me now?